So there's a lot we can do with an overall reaction like this one if we know for sure what those elementary steps are. And so here we're assuming we already know the elementary steps. Those are written in pink. We talked about them. We can then, of course, identify whether it's unimolecular or bimolecular, simply depending on whether it's one thing or two things. And then the molecularity, as long as we're talking about a elementary step in a reaction, then the molecularity is the order of the reaction, which means that if it's unimolecular, then of course sort of intuitively that means that only one of these things, it's only dependent upon itself, and so the rate law would be first order. And so we could write a rate law, and so the generic rate law would just be rate is equal to K times A. For this specific step, we could write that as K times the ozone constant. Same is true for the second step. We know this is elementary, so we can identify its molecularity, which is bimolecular. And if it's an elementary step, then the molecularity is the rate law. So we could write a generic rate law, like rate is equal to K times A to the second power. It's important to note, though, that there's another option here, and that's actually what's depicted in this elementary step. You may say, well, how is that A? This is an example of a second order rate law, but of course there's another way to write a second order rate law, which would be A times B. And if both of these are first order, then the overall reaction order is second order. It's still a bimolecular reaction. The difference is, in the first example, two different A molecules have to collide to produce the product. In the second example, an A molecule and a B molecule have to come together. Both of these are second order bimolecular type reactions. Of course, the specific flavor that we have here is the second type because we have two distinct molecules. So this would be the actual rate law for the elementary step as depicted. So why is this useful? Well, remember, this reaction, the net reaction, which is the sum of the two elementary steps, there is nothing that we know about it. If we didn't already know what the elementary steps, there's nothing that intuitively tells us what type of system it should be. Remember, the only way we were able to derive a rate law for a net reaction was what we did in the past, and that was via experimental data. We used this method of initial rates in that table, and that allowed us to determine what the order of each of those reactants were, and then we could build an experimental rate law. What we're doing here is circumventing necessarily that need. If we have a reaction and we know its elementary steps, then we can write a rate law for each of those individual elementary steps.